Okay, so here's a nice problem that came up on the Stanford Math Tournament, and I'm going to present a solution that uses the roots of unity filter. So the problem is to evaluate the sum from n equals 1 to infinity of -1 to the n plus 1, divided by the quantity 2 and choose 2. So the first thing you want to do is you don't like 2 and choose 2, so you want to turn that into something that you can work with better. So you know that 2 and choose 2 is going to be equal to 2n times 2n minus 1 over 2. So we can rewrite the sum as twice the sum from n equals 1 to infinity of -1 to the n plus 1 times the quantity 1 over 2n times 2n minus 1. And this one is pretty bad. Okay, so now when you see an expression like this, the first thing that you always want to do is try and use a partial fraction decomposition. So you can pretty easily check that this expression is going to be equal to twice the sum from n equals 1 to infinity of -1 to the n plus 1 times 1 over 2n minus 1 minus 1 over 2n. And so that's just decomposing that. And so ideally, when you have something like that, you hope for something that telescopes. So let's write out the first couple terms of the sequence and see what happens. For now, I'll ignore the 2 and then I'll throw the 2 back in later. So when n equals 1, this -1 becomes -1 squared, which is 1. And so what you get is, or actually I'll throw in the 2 now, 1 over 1 minus 1 over 2. And then when n equals 2, this becomes -1 to the power of 3, which is -1. So that means that it's -1/3 plus 1/4. When n equals 3, it's -1 to the power of 4, which is 1. So that'll be plus 1/5 minus 1/6. And then you can check it's minus 1/7 plus 1/8 plus 1/9 minus 1/10 minus 1 over 11 plus 1 over 12, and so on and so forth. So hopefully you can see a pattern, and that is, it looks like positive, negative, negative, positive, positive, negative, negative, positive, positive, negative, negative, positive. So it's some pattern that repeats every 4 terms, and we want to evaluate this sum. So if the pattern were to repeat just every 2 terms, so it's positive, negative, positive, negative, positive, negative, then you probably have seen that you can evaluate it using the Taylor expansion of the logarithm, the natural logarithm. So that is that the sum from n equals 1 to infinity of x vn over n is equal to negative ln 1-x. There are many different ways to write this series expansion, but this is one of the ways to write, and this is just convenient for what we're going to do later on with this. So if it was positive, negative, then what you can do is substitute x equals -1. And then on this side, you get -1 to the n over n is equal to negative natural log of 2. And then because the first term here is negative, because you have -1 to the power of 1, you can just multiply both sides by -1 to get rid of that. But instead we have something where it's positive, negative, negative, positive again. And so we want to somehow isolate every 4th term and give it an associated sign. So that's something that I did in my video about roots of unity filter that I explained. And so what we have here is some function f of x, which has a series expansion. And what we want to do is isolate a0 minus a1. I'll actually write it like this. a0, there's no a0, is there? a1 minus a2 minus a3 plus a4 plus a5 minus a6 minus a7 plus a8, and so on. And so what we're doing is we're isolating every 4th term and make it positive, negative, negative, positive. And so I said at the end of the video that if you want to isolate every term which is a mod 4, you just multiply f of x times x to the power of negative a, and you do your sum over things. So what that means is a1 plus a5 plus a9 and so on. That is going to be equal to 1/4 because you're doing it mod 4 times the sum of your 4th roots of unity of, just call it z instead of x, so it's more natural with complex numbers, z inverse f of z. And then if you want to do minus a2 minus a6 minus a 10 and so on. Well, this is just negative 1/4 times the sum of your fourth roots of unity, z to the minus 2 f of z. And you may see where the pattern is going. The next one would be negative 1/4 sum of z to the minus 3 f of z. And the next one would be positive 1/4 the sum of z to the minus 4 f of z. Now z to because you're taking every fourth number, instead of doing z to the minus 4, you could also just replace it with 1. And also because you're taking fourth roots of unity, since z to the power 4 is equal to 1, z to the power minus 4 is also equal to 1, so it doesn't matter if we get rid of that. Now we're looking for the sum of these four things. So what we could simplify this to is say that our sum that we want up here is going to be equal to the sum of over all roots of unity, so z to the power 4 is equal to 1, 1/4 times f of z times the sum of these guys. So that'll be z inverse minus z to the minus 2 minus z to the power of minus 3 plus 1. So yeah, this is going to be equal to this sum in here. And because we're multiplying this by 2 to get your sum up there, I'll just replace this with a 1/2. Okay, so now I'll erase some of this and write this up here. Okay, so we have that this sum is equal to the sum of 1/2 f of z times this stuff, where f of z has this series expansion. And what this will do is this will isolate every four terms and give it a sign of positive, negative, negative, positive. I just put the 1 up front instead of at the end because it seems more natural. So let's write this explicitly. So this will be 1/2. Let's just move this minus sign out to the front. And that'll be f of 1 times 1 plus 1 minus 1 minus 1 plus f minus 1 times 1 minus 1 plus 1 minus 1 plus f of I. This is where we have to check things a little bit. 1 minus I, this will be negative 1, so that'll be plus 1. And then this will be I to the minus 3, so that'll be 1, 2, 3. So that'll be I, and then you subtract off. So that'll be minus I. And plus f of minus I. And you can check all these again, but you can also think about it as like, since these are all real coefficients, all you take is the complex conjugate of everything. So this will just be 1 plus I plus 1 plus I. And you can check that that works out. Okay, so let's start to evaluate these. F of 1, natural log of 1 minus 1, infinity. That's already a problem. This is 1 plus 1 minus 1 minus 1, which is 0. And we are already stuck. So one way to avert the issue is just say like, okay, f of z times this guy is continuous. So what you can do is you can just take the limit. So you can take the limit as z approaches 1 of negative natural log of 1 minus z times 1 plus z inverse minus z to negative 2 minus z to negative 3. And I'll leave it as an exercise to you if you want to check it, that this actually evaluates to 0, which makes sense because none of these terms will end up being infinity, and the sum is finite or presumably finite because they're asking it to you. And so this should be finite, and the only like reasonable finite answer would be 0. Well, I guess that's not true, but 0 is nice. So this term we can ignore. Now f of negative 1, actually we don't even have to evaluate that because 1 minus 1 plus 1 minus 1 is 0, so we can also ignore. Let's see what we have now. Negative 1/2 times 2 minus 2i times the natural log of 1 minus I, and oh wait, I should not have put the negative sign there. So yeah, I just put S here. I plan to put natural logs there, but now I'm putting natural logs, so now I'll take the negative sign out. So this is 2 minus 2i, natural log 1 minus I, which comes from this term. And then this term is plus 2 plus 2i times natural log of 1 plus I. Okay, so now let's isolate the real and imaginary coefficients on the outside. And let's actually multiply and divide out by 2 because that doesn't really do anything. So what you end up with is negative negative 1, yeah, so this becomes negative quantity natural log 1 minus I plus natural log 1 plus I. And so that's just grouping together 2 and 2 and putting these 2 and I and them together. And then we're just multiplying the 2 by the negative 1/2, and that'll just become negative 1 on the outside. And then we can add I and do this term minus this term because we have a positive 2i, negative 2i here, and again canceling out the 2's. So that'll be natural log 1 plus I minus natural log 1 minus I. Okay. So now we want to evaluate this. Well, we can group these two together by using the fact that the sum of the natural logarithms is the natural log of the product of the things. So this will be negative natural log of 1 minus I times 1 plus I. And then this will be minus I times the natural log of the difference of these two i's. And again, you can use the fact that the difference of the natural logarithms is the quotient of the natural logs. That is the quotient of what's on the inside. To be 1 plus I over 1 minus I. And yeah, okay. So now this, fortunately, ends up to be 1 minus I plus 1. So this just becomes 2. So this will be negative natural log 2. This, on the other hand, is a bit more interesting. So 1 plus I over 1 minus I, you can check that however you want. You can do complex conjugation on the top and bottom and figure out what it is. Or you can see that these two have the same magnitude, so you can look at the angles. Any way you do it, you get that this is minus I natural log of I. Now we run into a problem because we have the natural log of an imaginary number, and the natural log of an imaginary number generally is not defined. So how do we avert this issue? Well, the easiest way to just explain it off is by saying that the terms that this come from must evaluate to something, and so this is in general multivalued, so this can honestly take on any number that looks like pi on 4 plus 2 pi times I. And if you take e to the power of any of these numbers, you're going to get I. So the natural log of I can be any of these numbers. So the problem is figuring out which one of them it is. So the way to argue that is here, we get these I terms from the second and fourth terms of the series. And so if you look at the second and fourth terms, that'll be like 1 over 1 minus 1 over 3 plus 1 over 5 minus 1 over 7 plus, and some stuff from there on forth. So these must obviously converge to something, and they actually sort of correspond to using the roots of unity filter on natural log 1 minus z of this. And this sort of natural logarithm has the property that it's continuous. And so you can think of this as sort of measuring the angle here. So this corresponds to the natural log of some expression with respect to z. And that expression won't converge anywhere here, but it'll converge for the positive real numbers. And so for this one, obviously the natural log of 1 we want to be 0. And so if we increment this by a little bit, because this expression is actually determined from evaluating the series expansion of something at I, and series expansions are continuous, this quantity over here will be some I theta, where theta is very close to 0. So what that means is it won't be like, if this is like say pi divided by 100 radians, this will be pi over 100 if you take the natural logarithm from the series expansion. as opposed to something like I times pi over 100 plus 2 pi, because this needs to be continuous, so this needs to be close to 0. And so from the same continuity argument, you can like sort of progress this little by little until you get to I, and you realize that this actually must be I pi on 4. So for example, if you think that it might be something, or sorry, I pi on 2, not pi on 4. So if you think that it might be something like minus 3 pi on 2, that would mean that you have to go from here and continuously move up to this point up here. But the problem is that your natural log of -1 is undefined in this power expansion. And so again, this power expansion just somehow modifies to give you this. And so because this must be continuous, you get that the only possible answer is pi over 2. And that's again because this gives physical meaning to that 1 minus the third plus the fifth minus the 7th series. So finally, our answer just becomes I times minus I is going to be equal to 1. This will be I on 2 minus the natural logarithm of 2. And yeah.